All right, let's move on to Chapter 5. Chapter 5 covers venting, which is something that honestly is probably as critical as anything you're going to do in furnace installation or even in service. So let me get this pulled up. This is Chapter 5 in your textbook, and then there's also some other material on the module. So kind of run through this real quick. So I know these are kind of running through the chapters, and it may seem like I'm just repeating the slides or repeating the book, but there are some little things that I'm going to throw in as we're going through this. So try to watch these and pay attention. It's not just, hopefully, not just reading the slides, but kind of expanding on it, I guess. So we've already talked about draft. We've talked about flue gas, byproducts of combustion. Um, Proper combustion, improper combustion, both of those, regardless of what the furnace is doing, has to be exhausted outside. And so um, you have to find a way to get rid of those. Natural draft and mechanical draft are something that we've talked about um, a little bit, and at least reference those. So kind of explain the difference. Natural draft. There are still a lot of natural draft furnaces and boilers out there. We actually have a natural draft boiler in the lab, so you can kind of see how that looks compared to the forced draft systems that we're using, or the induced draft mechanical draft systems. So natural draft is just basically using um, convection currents, hot air rising naturally, just trying to go upward and using that buoyancy of that hot flue gas to create movement and go out the stack. So it's obviously not as effective at getting rid of everything because you're not forcing it out, but it's kind of the way it's been done for a long, long time. A lot of water heaters you'll still see that use natural draft. So something else to kind of consider there. Even if your furnace is forced, your water heater could be natural. So kind of explain those. And then mostly what we're going to deal with um, is induced draft systems. Induced means that you're actually pulling the air through the exchanger, and forced means you're actually pushing it through. So negative pressure in an induced draft system. So your pressure switch is going to measure a negative pressure. Once it gets to a certain pressure reading, then that switch is going to make and allow it to go to the next step. Forced draft systems are the opposite. They're pressurizing that chamber. They're forcing air into the chamber and through the chamber and out the flue pipe, whereas induced draft is actually pulling air through it. And so you may think, well, what's the big difference? Why would they do one versus the other? Um, a few different theories on that. The main one I can kind of think of and that I've heard, induced draft tends to be the way that it's done because if there was a chance that you had a leak, you had a cracked exchanger, hole in your exchanger of some sort, it's more likely if that's a negative draft system that you're going to pull in air from around it, pull in your return supplier, your house air going through your furnace. That negative draft on your exchanger is going to pull that air in versus a forced system where it's positively pressurized is going to push that possible CO out into the house. So there's a little bit more safety factor into the negative pressure because it's less likely to make it into your house because it is under negative pressure. So kind of the way I've always kind of looked at it anyway. You don't see a lot of forced draft stuff, or at least not in residential. Commercial boilers and stuff, you may see some forced draft boilers, but don't see a lot of them in furnaces. So, as we've said before, always refer to manufacturer's literature and any other codes that you got to deal with. Local codes, national codes. So, Journeyman Prep, we're going to talk about uh, the IMC, which is the International Mechanical Code, and the NFPA 54, which is the National Fuel Gas Code Book. And so those are both some of the national guidelines, the International Code Council books, but always go by the manufacturer's literature if possible, because those books should follow, if not exceed, um, the requirements of the code, the national codes, state codes. So always go by those first, from at least from my experience, and then you can also look at local codes, national codes. All right, so we've already talked about combustion and the things that can be produced, carbon monoxide, CO2, the byproducts of combustion, flue gases, and the things that they contain. So not necessarily CO present, but very possible. That's the big one. But even if it's just normal combustion and you've got CO2 and water vapor, and you don't want those coming into your house, obviously, and you don't want them coming back into your house through an opening, maybe a window or something that it's drafting back in. So you've got to be able to vent this properly. All right, so different categories of venting, as we've already talked a little bit, high efficiency versus standard efficiency, non-condensing versus condensing gas furnaces. So condensing gas furnaces are trying to remove as much heat from that flue gas as possible before they send it outside. As a result, you're going to run a much lower vent temp. So a high efficiency 90 plus furnace is going to be, the easy way to tell is you're going to have PVC pipe running out, or you should have PVC pipe running out the vent. That's your vent material. Whereas a standard efficiency 80%, you're going to have a higher vent temp, and so you're now looking at not condensing that. You're wasting more heat that you could, that a high efficiency furnace could have captured through a secondary heat exchanger, but it's letting it go outside. So as a result, you have more heat that's going through that pipe. You're going to run, if you run that furnace, and I think there's a video that it's on Blackboard, or that you can find, I found on YouTube, that a guy actually put the PVC pipe on an 80% furnace, and within just a few seconds, that pipe just completely melts down. So it's imperative that you put the right material and that you install it the correct way. And that's one easy way to tell. Like if you're looking at a furnace, that's a dead giveaway. If it's got a metal pipe, it's an 80%. If it's got PVC pipe, it's 90 plus. So you might think, well, why couldn't you run PVC, or why couldn't you run metal with all of them? Because if metal will handle higher condensing temps, then it would handle lower, right? And so you may think, well, why couldn't you run a 90 plus through metal vent? A condensing gas furnace is running right on the borderline of condensing. Even though a lot of it condenses maybe in the furnace, as it goes through that pipe, any flue gas, any water vapor that makes it into the vent, once it cools down just a little bit, it's going to start to condense as well. So you have to have a way for that water to get back to the furnace and be drained out. It's because you're going to produce water. And so if you have a metal vent and you have water, and another thing is that water vapor is potentially slightly acidic, and so it will corrode a metal pipe like crazy. So not only just because it's water, but because it is corrosive, because it's just the way that it goes through the combustion process. So that vent has to be PVC, and it has to slope back toward the furnace so that any water that is collected in that is going to make it back to your drain. That a furnace, condensing furnace, has its own drain. So we'll get into different types of furnaces and applications a little later on, but just to give you a realistic difference there. So your different categories of furnaces. Category 1, these are mainly going to be, I'm going to say you're not going to run into these a whole lot. These are atmospheric draft. These are natural draft. And maybe some lower efficiency fan assisted, forced or induced systems. They're going to have an efficiency of 65 to 83%. So that's meaning that for every, the efficiency is measured in, for every ounce of gas you put in, every BTU of gas that you put in possible, how many BTUs of heat are you getting out that can actually be used at the house versus how much is getting sent outside. So a 65% efficient furnace is wasting 35% of the heat. It's sending it right out the flue. And so the closer you get to 100, the more complete your heating efficiency is, to where you're using almost everything you can. You're not going to get it to 100, but a lot of the furnaces they're running now are running 97, 98%. So they're getting as close as they can, but you still have to have a little bit of waste because you have to have a flue. You have to have a vent to get rid of the stuff you don't want. So atmospheric draft is you're going to run 3, maybe 400 degrees. It's going to be very hot. Obviously, you're not going to stick your hand to that vent pipe. Fan assisted systems are going to be a little cooler, but still you're going to be running 250 plus. And it talks about temperature rise across the furnace. So it's something we kind of talked about in the last lesson a little bit. So here's some examples of category 1. And there are a lot of these still out there. I've ran into a lot of older furnaces that look just like these, boilers as well, that are in people's homes today, and they're still running. I can think of several offhand that look like, the one on the left and the one in the middle there. So the way they're running is they don't have a fan. They actually are using that natural draft into this this compartment here that's called a vent hood, and it's just capturing that light, buoyant, hot air and letting it go out the pipe. You'll notice this one has a damper on it as well. This one doesn't, but so these are still out there. You're still going to be working on these probably. So you need to know that at least they exist, but you're wasting a lot of energy there. So that's a good sales point is if you know the efficiency that furnace is that it's supposed to run. And then let's say you could figure out how to do a combustion analysis to see what it's actually doing. You could calculate how much fuel they're wasting every year, every month, whatever, based on their efficiency. If they're 65% efficient, if they're inputting 100,000 BTUs of fuel, but they're only getting 65,000 BTUs of heat out of it, you can do the math pretty quick and say, okay, you're wasting 35%. If I were to sell you a 90 plus, we could get that down to 5% waste, and then you could put a dollar figure on that pretty easy and say, if you reduce your waste by 30%, how much would it save you over the course of a heating season? So that makes a pretty easy sale to upgrade people when it's time to upgrade. So like I said, these are very inefficient, but they are effective. They do the job. They seem to last forever, it seems like, those old ones. A fan assisted, still, you're looking at your metal pipe. Now you'll notice on these, if you look at the top, so you've got your furnace at the bottom, and then on the top of all 3 of these, you've got an air conditioning coil. So one thing that's different about a furnace and AC combo versus an air handler setup, like we're going to see in heat pumps and AC systems, is heat pumps and AC systems are using, usually they're using an induced draft. I say that term, but they're pulling through the coil, through the AC coil. So the coil is below the fan. So the fan is actually pulling the coil under negative pressure. Furnace and AC coil setup is usually positive, whereas a heat pump air handler is negative pressure on the coil. So that coil is having air drawn through it versus on a furnace setup like this one, you're actually forcing air through it. It may not seem like a big difference, and it's really not, but it does affect some of the ways that you install it and some of the ways that the system's going to react. Another thing that makes it a little bit hard, as you can see, if there was a breakdown of this, you could see a little better, but if you were to take the panel off of this coil, so inside of here, you've just got a traditional A coil. So this is what we would call a cased coil. So it comes cased. It's got a casing around it, sits on top of a furnace. You're going to want to size that to fit that furnace if at all possible. Match that up as best as you can. You can install furnace and leave the coil, leave the outdoor unit. A lot of times people will do that. Their furnace goes bad, but their air conditioner's fine, or vice versa. Their AC goes out, but their furnace is fine. So you can mismatch those, but if at all possible, I like to match things up. Plus, it means more revenue for you, and that way you know that everything is made for each other. But you take that cover off, and inside of there, you just got an A coil, or some sort of maybe an N shape, but you've got a traditional looking air conditioning coil. It's just sitting on top. And so, as I mentioned before, in the last lesson, one of the things that can cause your furnace to fail is improper airflow, to where coils are dirty, fans are dirty, filters are dirty, you're not moving enough air, your duct's undersized, whatever. And so it's a little harder to get to things like that because, as you can see, this coil, if it's an A coil or whatever it is, you can't just get to the bottom of that because it's sitting right on top of the furnace. It's attached to the ductwork, and so it's a little bit harder to just inspect that and say, oh yeah, it's really dirty, it needs to be cleaned. And it's even harder to pull it. So usually what you're going to do here, and we'll kind of go through this in lab, is you're going to pull this cover off, remove the screws out of this cover as much as you can. The flue pipe's in the way, you might have to move the flue pipe, depending. But if you had to clean that or inspect that coil, and then inside of there in your A coil, it's just two panels of coil material, shaped like a triangle or an N or whatever it's shaped like. And then there's going to be like a metal plate on the end. You pop that plate off and you can see right up inside of that coil. So a little harder to inspect. That's why a lot of people don't end up doing it, because it's harder to get up in there. So filtering these is a big deal, because if you have to start tearing one apart and clean it, it's a pretty big job. Category 1 venting materials can be 26 gauge single wall pipe or double wall B vent. So single wall and double wall. This is what I'm going to refer to as B vent. So anytime somebody says B vent, they're referring to a double wall locking type pipe system. And then single wall pipe just basically is a piece of metal rolled up. So there's some limitations on how far that you can run single wall pipe. If at all possible, you like to run B vent as much as you can, and then but it's harder to work with. It's harder you can't just cut it and size it if you got a short run, so you can use single wall pipe in between that. But the advantage of this is you've got this extra barrier to where you've kind of got an air barrier that's keeping that from getting too hot. It's also keeping it from picking up or losing heat, I guess, to the outside. And so it's gaining some of its, keeping some of its efficiency while also keeping that a little bit cooler. But category 2 furnaces are going to be 80 plus, 83%. It's not something that you're going to run into a whole lot. And so I'm not going to spend a ton of time with this. Honestly, I can say I don't know that I've ever seen a system like this. Category 3, fan-assisted systems, still running 280 degrees plus of flue gas temp. You got some unit heaters, furnaces, stuff that fall into that category. And so you'll see a lot of these in like warehouses, shops, factories, garages, places of business kind of thing, greenhouses. Venting materials they're using. All right, category 4. All right, so here's where we get into our high efficiency stuff. So up until this point, probably more category 1 and category 4 stuff is what you're going to see. Category 4, this is what we're going to call 90 plus. They're saying at least 87%, but typically over 90 plus furnaces. They're fan assisted with a positive vent pressure. So everything is being forced through the vent, but you're still probably using a induced draft blower to pull through the exchanger. So they're saying positive vent, meaning the vent itself is positively pressurized, not the heat exchanger. Your flue gas temps, 100, 120, maybe even less. You may even run in the 90s, depending on how efficiently you're burning. And so, you don't want to get it too cold, obviously, but you're going to be running 100 to 120 degrees versus 300 degrees on a category, on a 80%. So all of those degrees are BTUs, right? And all those BTUs is gas, and it's all wasted. And so all those pounds of gas are money. So the customer's paying for that, whether they realize it or not. And so, like I said before, if you can talk them into an upgrade, it may mean increase in sales for you, but it also means increase in efficiency for them. So that's something that is, in my opinion, a fairly easy sell and it makes sense. Like if I was installing a gas furnace with an air conditioner system and I was wanting to invest in efficiency, but I just didn't have a ton of money, I usually tell people I would rather invest in a furnace, um, a more efficient furnace, than I would maybe a more efficient AC system. Because if you're just running air conditioning through the summer and then you're running your furnace in the winter, uh, ACs are, you're going to save some money even with a higher efficiency setup, but all those aren't going to be too bad. Anything over 14, 15 SEER, any modern equipment is going to be pretty efficient. But your heating season, that's when you start to see the difference. And so I would tell them I would invest in a good furnace because not only is a good furnace going to be more efficient on gas, but if you upgrade your furnace, you're maybe talking ECM variable speed type blowers, which is going to help you in cooling as well. So you might see that savings more year round than you would with an air conditioner that's only running half the year. You can run a furnace with a heat pump, but normally you don't see it a lot. So usually I'm just talking about an AC and furnace setup. So as I said before, you can see here some different applications, different setups, but they're all kind of doing the same thing. You'll notice that some of these have a pipe coming in, or two pipes, and some of them have one pipe. You also notice a drain on the top of these. That's just a drain for your AC coil, that 3/4 inch pipe. Um, all right, so what you're looking at here, and I'm not sure which is which because I don't know which side this is bringing it in and taking it out on. I would say it's um, intake. I don't know for sure. I'd be guessing. Probably intake in the middle, exhaust on the right. And so if you have a furnace that is in a fairly confined space, and honestly, it's when you actually do the math on how much combustion air you need, usually needs to be a bigger space than what you'd originally think to have enough free air available for combustion. So if this is in a closet, it's in a mechanical room, something like that, you're going to need to pipe in outside air. Um, so you're bringing in fresh air and then you're exhausting your combustion air. This one on the right, they apparently have enough free space. Maybe it's in a basement or something. And so they're just drawing it from the room and then venting back outside. So they've only got one. But these two are pulling outside air in and then exhausting combustion air back out. And you'll also notice that it's a little harder to see on the other two, but um, there's an additional drain on the side of this furnace because this is a condensing gas furnace. It's going to produce water. So that water has to go somewhere. You have to get rid of it. And so you have to have a drain set up. It has to be a special drain set up for that furnace. All right, so a high efficiency furnace produces water through the winter. So you got to have a way to get rid of that water, and you got to take freezing into account. If this is in a place where it could freeze, it's in an attic, I wouldn't traditionally put a condensing gas furnace in an attic because you're going to deal with freezing issues. Crawl spaces are sort of iffy depending on how well the crawl space is insulated. You may have to take some steps to winterize that, um, heat tape on your drains, that kind of stuff. So there's cases to where even if it would be more efficient to put in a high efficiency furnace, it's not feasible because of the condensing factor. So you really have to keep that in mind because you're producing quite a bit of water, and that water has to be piped to a drain. So you could run it to a condensate pump. Some manufacturers recommend that condensate pump be a special type pump that's made for this because of the possibility that water is slightly acidic. It can cause those pumps to fail pretty quick, but a lot of people are running them just to a straight condensation pump like what you see here that you could buy at Lowe's or anywhere else. So all those do is dump the water in, and then once they fill up, there's a little switch in there that kicks it on and it pumps out a hose. Category 4 bending materials, you got to use PVC. It's got to be glued. Um, I'm not sure the schedule. I think it's got to be schedule 40. Um, it's got to be the thicker. It can't just be the drain type, like what you'd use for sewage or like septic or something. It's got to be the thicker PVC that you're going to get. And when you're doing this, it may seem kind of self-explanatory, but you're going to want to clean that up as much as you can. Use a saw or a sawzall or whatever, but you're dealing with usually 2-inch to 3-inch pipe, and a lot of that's going to depend on manufacturer specs, what they recommend that you install. Most of them are going to come with a 2-inch opening, but you may have to upsize it for 3-inch pipe because of static pressure buildup in that pipe. So you're really going to want to refer to manufacturer specs on how far that you can pipe that with 2-inch pipe. If you go very far, you're going to build up back pressure in that pipe because of friction, and it's going to cause your pressure switch not to work right over time. Could cause your furnace not to run all the time. I've ran into this a couple of times to where maybe I was using an existing vent. I can think of one example right offhand to where I just used an existing vent that was on the last furnace. Everything seemed fine about it, and didn't really maybe look at the specs like I should. I just assumed that it would work, and hooked that 2-inch pipe back up, fired it up. It was summertime. I fired it up to make sure it would run, and everything was fine. Everything ran. And in the winter, I get a call back that says that the furnace ran for a little while, and then it's just kicking off. It won't kick back on. It'll run for a while, and then it kicks off and won't run. So um, show up, and it's off on a pressure switch failure. Come to find out, that furnace needed the pressure switch on that one was a lot. Um, it needed a lot deeper vacuum or negative pressure than the last one did, and so because of that pipe wasn't capable of moving enough air, basically. So I had to upsize that pipe. So I had to go. So it said in the specs when I got to reading into the manual, if it exceeds this many feet of run. Another thing to take into account is, let's see if it says this. Okay, so I'll get into this here in a minute. I thought it was in here. So you have to take into account your elbows because your elbows count. They restrict a lot. So in that case, what I ended up having to do was I had to upsize. I had to get my 2-inch pipe so far up and then expand it to 3-inch so that 3-inch pipe has a lot more room to move that air, so it reduces my pressure, my back pressure a lot. So always refer to the specs. The So as we mentioned before, part of the purpose of this pipe is not only to get rid of the gas, but it's to take care of the water. And because this is running at such low condensing temps, you're gonna get condensation or such low combustion temps, I guess. That it's really close to the condensing point of that water. So if it cools down even a little bit, you're going to get more. Let's say this is running through a basement or a crawl space, and it's as soon as it leaves the furnace, obviously that pipe is colder than it was in the furnace, and so you're gonna lose heat to the surrounding air. It's not insulated or anything like that. It's not supposed to be. So you're going to start to condense. You're going to get water. That water has to go somewhere, and you would think, well, I'll just make it go outside, but that's not the way that you do it. It goes back to the furnace. So any water that's picked up in that pipe will drain back to the furnace, go back through the drain system in that condensing gas furnace, and go out the drain into the condensate pump or into the floor drain or whatever. So you have to make sure that you have a slope on that that's going back to the furnace. Proper pitch and slope of the vent is a 1/4 inch per foot or an inch for every 4 feet. Um, so you have to have that kind of fall back to the furnace. You don't want to have, you want to make sure you have supports, because if you let that sag, you can get like a belly in there to where that creates like a trap, and that can cause issues as well. So you want to make sure that you're running it straight and that everything's supported well. PVC pipe elbows, as I mentioned before, couplings, elbows, you want to try to avoid those as much as you can. And so this gives you an example of a maximum allowable length of flue vent pipe. And so this, let's say for this example, this is a 3-ton AC with, let's see, with 70,000 BTUs. All right, so this particular furnace here, I'm just going to go by the second row. Whoa. Second row here. It says I could use 2 or 2.5-inch pipe. Now 2.5 is kind of an odd size. But with that, it says that I can run, let's see, make sure I'm reading this right. Maximum allowable length of flue pipe. So I can have, if I have 4 elbows, I can run 62 feet of pipe. Now this chart's broke down a little bit different than the ones that I've dealt with. Usually, what it'll say is you have to have a total, what they call a total equivalent length, and each elbow or each fitting counts for a certain amount of feet. So, for example, let's see, yeah, it didn't show it on here. So, for example, like a 90 may count for 15. I'm just making this up. I can't remember off the top of my head, but like one elbow may count for 15 equivalent feet. So basically, what it's saying is, if you have an elbow, that's the same as having 15 feet of straight pipe because of the restriction that elbow is placing. So try to avoid elbows if at all possible. Don't just, yes. Okay. Thank you. See you all. Yeah, give me just a second. Excuse me, guys. I'm going to have to pause this.